Hi, this is Big Tuition, and this is a quick review on the topic of sampling, hypothesis testing, and regression. For some reason, well, there was a typo for the title, so yeah, we'll correct that soon. In any case, these chapters are very GDC heavy, so like it's very calculator heavy, and most of the concept testers will be very qualitative in nature. As such, we'll just quickly run through the concepts and the notation, definition, etc. Alright, beginning with sampling. Sampling is basically the act of studying a small group of a larger population. And here we have three main concepts we want to start off with. One is the population. The population is a group of people or object, and usually this is like a group that we want to study. Next is the sample. The sample is the subset of the population where the data is collected from. And then the sampling frame. So sampling frame is a little bit more tricky because it sounds like the same as sampling, but it's not necessarily the sampling. It's not necessarily the sample. So if you draw a Venn diagram, what the sampling frame looks like is like, if this is the population, the sampling frame is like a portion of the population, and you take the sample from within the sample frame. Okay? So a sample frame is like a subset of the population that is being studied, but it is not necessarily the sample. And the sampling frame, ideally, you want it to be the population. But of course, most of the time we can only study a small part of the population, and we can only take an even smaller part as the real sample. So why do we sample? Because time or cost is too high to get information on the entire population. There is one very common problem. Sometimes it's impossible to sample the entire population, maybe because of practical concerns. And last but not least, it could also be because sampling destroys population. This is mostly in the study of like biology, when you take a sample of the cell, you always have to destroy the cell. Then that's quite counterproductive if we just sample everything, because we destroy everything, right? So a good sample must be representative of the population and must be fair and unbiased. These two are very important conditions for deciding whether if your sample is considered good or not. So representative means that it must represent all like smaller subgroups of the population. So if we want to do like a general sampling of the whole population, we need to consider whether if we are sampling all the age group, both gender, whether if they are high income, low income, and we need to consider all these problems for it to be representative. And sometimes it is also related to fair and unbiased, because if we are only sampling, let's say, the guys, then you will end up having a result that is very biased towards any issues that guys might have, right? So a good sample must be aware of being representative and fair and unbiased. The sample mean is the average of a random variable. This is basically the average lah. Okay? You have probably seen this many times before. You add all of them up and divide by n. If the random variable is normally distributed, then the sample mean will follow the normal distribution. Not just the sample mean lah, the entire sample distribution. Okay? The sample distribution will follow the normal distribution. If the sample have unknown distribution and has a large sample size n, by central limit theorem, the x also follows the normal distribution. That means when you have a large enough sample size, we can take it as being normally distributed. For that to happen, for central limit theorem, we want the n to be at least 30 to 50. Okay? So whatever you learn about distributions in the normal distribution also applies to here whenever your n is large enough. So if you have n of around 20 to 30, there can be a case made for normal distribution, but it's a little bit weaker. So it depends on the context of the question. You might still be able to apply the normal distribution, central limit theorem, okay? So yeah, that's the central limit theorem, right? So in the ideal case, the population and sample mean should be the same. Okay, this is 0.7 here. In the ideal case, they must be the same because your sample is supposed to represent the entire population. And so to calculate the mean is basically what is this summation is the same as what is written over here on top. Okay? So, however, Population and sample mean are usually not the same because the population, the n, number of objects will be different. So how it is related is that the sample variance is given by this 1 over n. There's a 1 over n involved here. Whereas for population variance, if we are trying to estimate the population variance from the sample, instead of dividing by n, we are using n minus 1. This is just one of the things to take note. Okay? And that pretty much sums up sampling. Moving on to hypothesis testing. So the hypothesis is a statement that we make about the population. It is a value, usually one of the population parameters, mean or variance. So we are basically making a hypothesis about population. Maybe we are saying that the population, the mean height of the population is, let's say, 190 cm. And the null hypothesis is what is believed to be the truth. Okay, it is usually the statement that is accepted to be true unless data strongly suggests otherwise. So maybe I say that the null hypothesis can be something, let's say the population, humans average height is not 190 degrees, 190 cm, 190 degrees. Okay, so alternate hypothesis is the claim that is to be verified. So in our case is maybe the average height of humans are 190 cm. So if the data strongly rejects h0, then we can determine by comparing the p-value of the test statistics with the level of significance. So testing essentially quantifies how strongly the data supports the hypothesis. However, one thing to take note is that students always have the misconception of a rejection being that the hypothesis is false. Okay? No. If there is a rejection of the hypothesis, it simply means that the hypothesis is unlikely to be true based on the level of significance, which we'll shortly cover. However, it doesn't mean that the hypothesis is completely false. It just means that it is not very likely. Level of significance is the probability of rejecting the hypothesis even though it is true. Okay? So we can reject the null hypothesis, but actually it turned out to be just the sample being a bit wrong, a bit biased. So it is still possible that the hypothesis is true, like what we have just said, but based on the level of significance, there are some probability of it being true, a small probability. This probability is set to be 1, 2.5, 5, or 10%. For a question, this is usually given. So the question will ask you to calculate or find out how likely the hypothesis is true or false to a level of significance. Either 1%, 5%, 10%, whichever they give. Okay? So in essence, hypothesis testing is basically saying that, hey, we are going to make a statistical guess about this population. How likely is it to be true or false? That's the entire gist of hypothesis testing. So p-value is the probability that the sample suggests that h0 should be rejected. h0 is the null hypothesis. This depends on the type of testing conducted. There are three types of testing. You can be one-tailed left, one-tailed right, and two-tailed. So here is one-tailed left is basically saying like let's say we have a graph like this, or average here in the middle. Okay, we want to test if, let's say, the chance is test if the parameter is actually smaller. So if, let's say, the mean that we find, usually we are testing for the mean, right? So let's say the mean that we find is here. Then we realize that, hey, the parameter is probably smaller than what we guess. This is the h0. Okay, this is the h0. This is the h0, and if our mean falls in this region, then hey, the null hypothesis is probably false, right? Because it is smaller than a certain p-value, where the p-value will be smaller than the level of significance, and in that case, we reject the hypothesis. So the p-value is simply a matter of what is the probability of the random variable x being smaller than the value x1. Okay? x1 is the number here lah, the mean that we find. Yeah, here is the value away from the distribution, right? Look here. Yep. Okay. So we can also have one-tailed, right? I believe this part there is a typo. Okay. So apologies for the typo. This part is actually a two-tailed test, and this part is a one-tailed test. So for a one-tailed test, right? One-tailed test, right, is basically seeing how likely it is for the null hypothesis to be for the actual parameter to be greater than the null hypothesis. So it will look like this. So if let's say our mean that we measure is here, how likely is it for the actual parameter to be in this area? Okay? Alright, so finally, a two-tailed test is when you are considering how different is the parameter from the mean. So if you are just trying to test how different the parameter is actually from the mean, then we need to consider both cases, whether is it larger than or smaller than, right? So in this case, we have to consider both ends of the probability. So whether is it larger than x1, whether is it smaller than x1 or larger than x1 on each side, okay? There's a negative sign. So this is the negative x1, this is the x1, okay? So the rejection or critical region is the set of value where the null hypothesis is rejected. Basically, if we are outside of this region, if our mean is outside of this region, we see that, hey, the null hypothesis is not very likely to be true. And therefore, we want to reject the hypothesis. This is a region away from the mean that has the area under the probability distribution function equal to the level of significance. The closest value of this region, this x1 and this x1 and this x1, are the critical values. So if the test statistics lies within the critical region, H0 is rejected at alpha level of significance, where alpha is what is written here. You see, this is the level of significance. Otherwise, H0 is not rejected at alpha level of significance as there's no sufficient evidence. Okay, this is how you answer your questions. So like, for example, if let's say they ask you how likely do you reject this question, like this hypothesis, this is how you will answer your question. Like, do you reject the hypothesis? You will say it's rejected at alpha, like 5% level of significance. Then that's how you answer. If you realize that it is not really rejected, then you have to say the null hypothesis is not rejected at, let's say, 5% level of significance, as there's insufficient evidence. Okay, so this is how you answer those type of word question, qualitative questions. Usually the distribution function used is the normal distribution function, and again, like what we just mentioned for sampling, if the distribution is not known and n is large, you should use CLT to approximate the normal distribution. If the variance is not known and n is large, sample variance and population variance can be approximated to be the same as normal distribution. Okay? Here is saying sample variance and population variance can be approximated to be the same. Okay? So, yes, so this is the gist of hypothesis testing. I don't think this part was explained super well. If there's a chance, I will upload another video on this. Okay, and next we have regression and correlation. When we gather a set of data that has two or more variables, it is usual to find any patterns to determine if there's any correlation between these variables. This is where regression and correlation comes in. So regression and correlation basically tell us how the two variables relate to each other. And this type of data with two variables are known as the bivariate data. The data are usually plotted on a graph as a scatter plot. So you'll look something like this. And usually a clear shape should be able to be seen if there is a correlation. So in this case, this is quite clear. There will be a linear correlation that looks like this, right? And no correlation looks like a bunch of randomly scattered dots. And in that case, you just have no correlation. So for regression, the point is you want to find the best fit line for the data. And correlation is about how strongly correlated are the data. So for regression, you are trying to find the line that is best fitting, which is then defined by the distance of the points away from the line. And correlation tells us how strongly correlated are the data in a given regression. Note that correlation does not imply causation. So maybe we can say that the math grade and the English grade, there are some correlation, but then that doesn't mean just because you're good at math means you're good at English, right? So describing a correlation describing with correlation is another qualitative question that you might be asked. First, you have to state whether if the relation between the two variables are linear, non-linear, or none. Is it a linear correlation? Is it a non-linear correlation, or there's no correlation? Then you have to state how the y variable change with an increase in x. So you can say maybe the y increases with x, or decreases, or there's no apparent change. Maybe it's a flat line. Okay? Here we need to do a recap on the independent and dependent variable. The independent variable is the control variable that is being controlled, being varied. Usually this variable have no error or uncertainty because it is being set. So for example, we can set how far a person can throw a ball, and the number of people will be how far a person can throw a ball given how long he's trained, right? Given how long he's trained. So if he's trained for 100 days, then the day is 100. It's not going to vary, right? It's an independent variable. Whereas the dependent variable is the variable that is being affected by the independent variable. So let's say it's the distance that the person throws the ball, and the distance is being affected by how well trained he is. So in this case, this is a dependent variable, it's affected. And here, because we are doing measurements, there can be error or uncertainty. So, of course, there are times where your independent variables still have some uncertainty associated with it, so it's not always guaranteed. But basically try and figure out which is the one that you are varying and which is the one that you are trying to measure, which is the one that is dependent, okay? When doing regression, the function that we use to model the data is called the regression function. When you try and fit the function to the data, we try and make the function as close to the line as possible. Or this line, I mean like the points that form the line. So this regression function, right, it sounds very atas, but actually it's just a matter of like what you choose. So you can choose it to be a linear regression function. You can choose it to be a x squared, so on and so forth. So this is it's just a function that you choose. The regression function is just a name for that function. Okay? So usually when we try and do regression, you'll be through least squares regression. Least square regression is when the sum of the squares of the vertical distance of the data from the line is minimized. When the function is plotted, the data usually does not fit perfectly, and we take the vertical distance of the data point from the function and square it I'll just do a quick sample. So for example, let's say we have a data point here. This will be y1. And then we have another data point here. This will be y2. And another point here. This is y3. What happens is in linear squares regression, we are taking y1 square plus y2 square plus y3 square, and we try and vary the line mx plus c until this y1 square plus y2 square plus y3 square, until this become a minimum value. This is what least square regression means. We see that y1, y2, y3 are actually basically just a distance away of the data away from the line that we are trying to fit. And when we are minimizing the distance, we are essentially increasing how good the line is fitting. We're increasing how good the line is fitting, right? And the reason why we want to use square, from what I understand, is just a matter of that you want all these values to be positive. And if you don't use a square, you end up having some positive, some negative, then you don't know if they are actually far away from the point or not, right? So when you try and minimize some positive and some negative value, it's hard to do it. But if you are minimizing a sum of all positive values, then it's relatively easier. So it's just a matter of convenience, as much as I know. Okay, so in essence, the function parameters are tweaked to minimize the sum. This is done behind the scenes in your calculator whenever you key in like a set of data. Don't have to worry too much about it. So when doing regression with non-linear functions, what you should actually do is to transform the data into a linear correlation before doing the regression. So for example, if you notice that the data point look like a x square, right? Instead of fitting the data directly, go and square all your x values first. So when you are fitting when you're fitting the y against x square, you should end up with a linear graph. So if you're fitting y against x, you will get something like a quadratic graph. But if you fit y against x square, in which like basically the coordinate here is x squared instead of x, and this is y, you should end up with something like a linear graph instead. Okay? So yeah, that's for co-regression with non-linear functions. Coefficient of regression for linear function is the gradient. It's basically like the gradient. Okay? Coefficient of regression is like the gradient. So we note that we can do a regression of y on x. Y on x basically tells us we are minimizing this y value here, or this y difference from the line. Whereas if we are fitting x on y, right, actually what happens is we are trying to minimize the x distance away from the lines. So yeah, so x distance away from the lines. And the formulas here should be all given in your MF26, I believe. Let me just do a quick check to make sure they are there. This is the estimated product moment correlation coefficient. So yeah, these are basically there. So actually no, this is not the same. Sorry, it's the next equation, the estimated regression line of y on x. So it's the bottom equation on page 6. So you notice they only do y on x. They only give you the equation for y on x. This is MF26. And for x on y, right, is essentially the same, except the denominator is changed to y. Okay, so if you are supposed to calculate for x on y, don't panic. Just use MF26. Switch the denominator from x to y instead. Okay, so if both y on x and x on y regression are carried out on the same set of data, the two lines will intersect at the mean point with an average x and average of y. Okay, so what happens is when you perform a regression, right, your your regression that is x on y and y on x may not always give you the same value, may not always give you the same graphs, sorry, but they will still, no matter what, intersect at the middle, which is the average of x and average of y. In essence, we can write it like this and this. So y on x and x on y. So you may see that this looks a bit like they look basically the same, right? But actually, I mean, B and D will be different lah. B and D will be different because they are also calculated differently on top here. Okay? So in the ideal scenario, actually, this and this should give you the same graph, actually, in the ideal scenario. But of course, because our sample is not always ideal, when we try and minimize them, they will end up becoming like skewed like this. So that brings us to how well our linear fit works, which is defined by the correlation coefficient R. Okay? Correlation coefficient tells us two pieces of information. The first piece of information is whether if it's positive or negatively correlated. This tells us the second thing is how good the correlation is. So positive, if the correlation R is more than 0, it means it's positively correlated, means when one variable goes up, the other variable goes up as well. If R is less than 0, then it's the reverse. When one variable goes down, the other variable goes down. Okay? And the magnitude of R tells us how good it is, how good the correlation is. If the magnitude of R is basically 1, we have perfect positive correlation. If it's 0, it means R has the fit have no correlation. And if it's negative 1, it tells us it has perfect negative correlation. Okay? This R is also given, is known as the product moment coefficient, something like that. Is in the MF26 as well. It's the one that I got confused with earlier, slightly earlier. So this is given. So right, for this type of questions involving all these funny equations, right? Number one is you don't have to remember the equation. Please don't go and remember the equation. It's quite painful. Number two, even if they ask you to calculate, they will give you, like, for example, this sum of xy, sum of x, sum of y, and then you just need to substitute the entire sum. Like maybe they tell you this is equals to 10, this is equals to 3, this is equals to 4, something like that. And then you just need to substitute all of them into equation. So this is really a matter of punching calculator. Okay? So one way to think about R is how close the x on y line and y on x line are. So remember we said that because the data sample is going to be like very scattered, your graph, your y on x and x on y, right, will result in two different lines. So if it's a perfect correlation can only happen one time in one scenario. It's like practically all the lines on the dot. Then if that's the case, R will be equals to 1 and or minus 1, depending on whether is it positive or negative, and the two lines will basically coincide. If R is 0, okay, in the most extreme case, if R is 0, then your two lines will look like this. It will just be one horizontal, one vertical. Okay? Basically that means there's 0 correlation. So you have two extremes. One is where the R is 1, perfectly correlated, and both lines overlap. And one is when R is 0, and you have one horizontal and one vertical line. Okay? This is the thing I was saying. Summarized data are sometimes given in questions. So this summarized data will basically be like sum xy equals to something, sum x square equals to something, and then you just need to substitute all this into your equations. So after we find the relation, we can use it to predict values of a variable when the other variable is given. Whether if the given variable falls within the original range of the data tells us if the data is being extrapolated or interpolated. So suppose we have a bunch of data that looks like this. Okay, suppose we have a bunch of data that looks like this. We managed to fit a very nice linear graph on it that looks maybe like this. If now we are told to predict 2 points, right? We are given this x and we want to know what is the y. And we are given this x. Okay, this x1, this x2, okay? And this y1, this y2. This is y2. We can see that the original range of x given is here, right? So for x1 we are interpolating, for x2 we are extrapolating. Interpolation basically means that we are predicting within the range of the data that was originally given, and extrapolating means that we are extending to beyond the data that we have. So we see that for extrapolation we need to be careful because the fitted function may not be representative of the outside range. For all you know, maybe outside this range the correlation breaks down. So for extrapolation you need to be careful. Whereas in the case of interpolation, the predicted results will be much more accurate. So sometimes they'll ask you, so is this a good prediction? Is this a good estimation? Then in that case you have to check. You have to check and make sure that, okay, this is an interpolation, it is good. Okay, and then you can, okay, if it's good, then sure, this is a reliable prediction, something like that. Okay, so for that we summed up these 3 very statistic and qualitative heavy chapters. If there's any questions, you can drop me a message on Telegram or in the form. And this should be the last part of the quick review series. Okay, with that said, I hope you enjoyed the quick reviews of all these pretty difficult topics, and as always, happy studying